In this video, we're going to talk about the limit comparison test. Consider the two sequences, a sub n and b sub n. Let's say they're both positive, they're both greater than 0. If we take the limit as n approaches infinity of a sub n divided by b sub n, and if we show that it's equal to some positive finite number L, then we can make this conclusion that these two series will both converge or they will both diverge. So let's say if we can establish that this series converges, then the other one will converge as well, as long as the limit of a sub n divided by b sub n is equal to a finite number. Or let's say if this series diverges, then the other one has to diverge as well, based on the limit comparison test. Now let's try an example problem. So let's say we have the series n squared divided by n to the 5th power plus 8. So use the limit comparison test to determine if this series is going to converge or if it's going to diverge. Now when n gets very large, the 8 becomes insignificant. So we can compare the original series to this new one. N squared divided by n to the 5th power. Now we can reduce it. 2 minus 5 is negative 3. So this is equal to n raised to the negative 3rd power. And so we can rewrite that as 1 over n cubed. Now, what type of series do we have on the right side?
P series.
Notice that it's a P series. And in that particular example, P is equal to 3. Now, what do we know when P is greater than 1? When P is greater than 1,
Converges.
the series will converge. So now let's use the limit comparison test to see if this is going to converge as well. So what we're going to do at this point is we're going to call this a sub n, and 1 over n cubed, let's identify that as b sub n. So we're going to take the limit as n approaches infinity, a sub n divided by b sub n. But instead of writing it that way, I'm going to write it as a sub n times the reciprocal of b sub n. So this is going to be the limit as n approaches infinity, n squared divided by n to the 5th plus 8 times 1 over n cubed. 1 divided by 1 over n cubed is the same as n to the 3rd power. So now we have the limit as n goes to infinity, n to the 5th power divided by n to the 5th power plus 8. So notice that the degree of the numerator is the same as the degree of the denominator, and that is it's both degree 5. And so the limit, when n gets very large, is simply going to be the ratio of these two numbers. So 1 divided by 1 is 1. So the limit does approach a finite number, in this case 1. So because it approaches a finite number, then both series must converge. So we know the first one converges, and so by the limit comparison test, the other one must converge as well. Now let's move on to our second example problem. So we have a series that goes from 0 to infinity, and it's 1 divided by the square root of n squared plus 2. So go ahead and use the limit comparison test to see if this series is going to converge or if it's going to diverge. So what other series can we compare it to? So let's eliminate the 2. If we do so, this is going to be 1 divided by the square root of n squared. And the square root of n squared is n. So we have the harmonic series, which is also a P series, where P is 1. And so if P is equal to 1, or if it's less than 1, then this is going to be a divergent series. So let's see if this is going to diverge as well. So this is going to be a sub n, and let's make this b sub n. So the limit as n approaches infinity of a sub n times 1 over b sub n, we're going to have this. Now b sub n is 1 over n, and 1 divided by 1 over n is n. So this is going to be the limit as n approaches infinity, and then n divided by the square root of n squared plus 2. Now what I'm going to do is multiply the top and the bottom by 1 over n. Now 1 over n is the same as the square root of 1 divided by n squared. And so this is going to be the limit as n approaches infinity, and then n times 1 over n, that's going to be equal to 1. And then if we multiply the things inside of the square root, 1 over n squared times n squared, and that's going to be 1. And then 1 over n squared times 2, inside the radical is going to be 2 over n squared. So now as n approaches infinity, this is going to be 1 divided by the square root of 1, and 2 over n squared, that's going to go to 0. So then this whole thing is equal to 1. So we know that this series diverges, and because we have a finite value, the other series must diverge as well. Now let's work on this example. So we have a series 1 over 3 to the n plus 5. Will that series converge or will it diverge? So the 5 is insignificant when n is large. So we can compare this series to this one. And so you can rewrite this as 1 over 3 raised to the n. So what type of series do we have here? Notice that this is a geometric series. And the common ratio is 1 over 3. So anytime the absolute value of the common ratio, if it's less than 1, then the geometric series, will it converge or diverge? If the absolute value of r is less than 1, the series is convergent.
Dang. I'm kind of hungry. Should have gotten some more snacks.
There's another orange right here. I bet you ate one home.
Yeah, but I get hungry. I'm a hungry man.
Here. And then the fruit. You want me to peel the orange for you?
I can feel it.
So now what about this one? Will that be convergent as well? Well, let's find out. So let's take the limit as n goes to infinity. A sub n times 1 over b sub n. So let's call this, as usual, a sub n. Now let's multiply it by 1 over b to the n. So if b to the n is 1 over 3 to the n, 1 over b to the n is going to be just 3 to the n. Now, when n is very large, the 5 is insignificant. So this expression turns into this one. We're going to get the limit as n approaches infinity of 3 to the n divided by 3 to the n. And ultimately, this is going to converge to 1. So once again, we have a finite value for the limit. So we know that this is a convergent geometric series. So therefore, by the limit comparison test, this must also be a convergent series. And that's it for this problem.
Greetings once again, AP Calculus BC students. It's a pleasure to be back with you for our final journey into Calc BC. We're looking at our topic 10.1 from Unit 10, which is all about our immersion into infinite series. And topic 10.1 is all about defining convergent and divergent infinite series. And as you can read from the slide, we're going to talk about reviewing some sequences and introduce the concepts of partial sums while focusing on convergence and divergence of both. So some of this might be a bit of a review from a previous course. Once again, my name is Anthony Record. I'm a AP Calculus teacher at Avon High School, just located west of Indianapolis. And as always, it's such a pleasure to be with you. So what is it that we are going to be learning? Well, I'd like to start off by just laying down the foundation for some basic terminology that's really important, because you're going to hear these terms and these phrases from the beginning of Unit 10 all the way to the end when Brian takes over and wraps everything up for us. So first of all, what is a sequence? Well, simply put, it's just a list of terms that are arranged in a particular order. Now we're talking about sequences that have mathematic type of features, so numbers would make a very logical type of sequence. So an example could be 1, 4, 7, 10, 13. And so as you can see, we could list each of these numbers and give them a name. The name I'm going to choose is A, and you'll notice that I have a subscript. Now the subscript I'm going to call N. We often will refer to that as the index, and that's just a way to very quickly determine who's who. If I say, hey, I want the third term in this sequence, you could very easily look and see that that would be 7. Those dots, sometimes called ellipses, not to be confused with the conic section, are going to indicate that this sequence is going to continue on forever. So we often like to consider this pattern that's presented, and we would really like to figure out a little bit more about it. You know, I've got 1, 4, 7, 10, 13. It's going to go up to some term A sub n. I'd like to know a little bit more about this. And so a lot of times we would like to come up with what's called an nth term expression. It's basically a formula, if you will, that will tell you how to find any term in that sequence, no matter where it's located. So we're going to call that our explicit formula that would generate that term. And then from our example above, if you played around with a little bit, and that's not really the focus of this particular video, we're going to be talking about that in some examples later on in some future videos, but that particular nth term expression could be 3n minus 2. You'll notice that for whatever n I decide to plug in here, let's say I want to plug in 3. 3 times 3 minus 2 is certainly going to give me that 7. And before I go on, I might mention this a couple of more times throughout our time together from topic 10.1 all the way to 10.8. And that is, the AP Calculus exam will very often use the letter K instead of N for its index. So you're going to see a lot of my examples kind of switch back and forth and sometimes use N and sometimes use K so that you get used to both. Well, we have some more basic terminology. Also, the idea of series. After all, that's what Unit 10 is really all about. And so a series is just the sum of the terms that appear in a sequence. An example, well, let's say I've got a series that looks like this, or a sequence of terms, I should say. 1/2, 1/4, 1/8, 1/16. A little bit more complicated than that previous sequence. Well, if I wanted to put plus signs in between each of those terms, instead of the commas, I have obviously a series. It's just simply a sum. Now, our interest is going to lie in studying infinite series, right? It's not a lot of fun to study a sequence of numbers that you can add together that have a finite number of terms, but it's a lot more interesting when you have an infinite number of terms. So specifically, we would like to investigate the behavior of this particular series that goes on forever and ever. Now, in order to be able to do that, we kind of need to understand this last term, the partial sum. And basically, a partial sum is just the sum of the first n terms in a series. Usually, we'll denote that by S subscript n. Now let's take a little bit closer look at the sequence of partial sums. And this is a nice geometric demonstration. It's likely that you had seen something like this before, maybe from your teacher. But let's start with a square that's 1 by 1. And I'm going to be very interested in figuring out what is my first partial sum. Basically, I want to figure out what is the area of that orange shape. Well, clearly we could multiply 1 times a half, assuming that I am going to split that square down vertically in half, and boom, I have that area of the orangish colored region. Now, if I continue that same idea, maybe take that white unshaded portion, split it in half, you can see that it's going to produce a square that's 1/2 by 1/2. And if I go ahead and take my previous sum, or my previous area, I should say, and add my new area, I now have my second partial sum. Basically, it's the sum of the areas of the shaded region of the figure. Well, let's just knock ourselves out and keep doing that. Let's take that white square in the lower right corner, cut him in half, assemble our third partial sum by taking our half that we had before, our 1/4 that we had before, and now we will add another area, the area of the green shape, which is 1/8. And we can do that basically over and over.
I'm falling asleep.
Over and over again, and just develop a new partial sum. In this case, you can see that that fourth term in the partial sum is 1/16. Well, like I said, if we add all these together, we would have the actual sum. And just with a little bit of common denominator arithmetic work, we can very easily come up with those values, as you can see. If this continued until, well, I ran out of room or colors, whichever came first, then I could conceivably say that I could have this pattern that develops, and it would go on infinitely. And then we wonder, what does this all equal? Well, I'll tell you. It equals 1. And the reason that it equals 1 is simply because we are going to consume the entire area of that 1 by 1 square eventually. But we're always going to be counting forever and ever to get there. Now, finding the sum of an infinite series is really based on this idea. And it says that if you've got a sequence of partial sums Sn, and you know that there's a limit of L, that infinite series will converge to that limit, and you can write it as any of these 4 expressions. These 4 expressions are all basically the same thing. And if the sequence of partial sums diverges, then the infinite series will also diverge. But where it gets exciting is if this infinite series here converges, then we will actually have a sum of the infinite terms that we can just call S. No need for a subscript because there really isn't one, because it goes on forever. So it's really important that you know that anytime that you see these 3 pieces of notation, they all mean the same thing, and that's the sum of the infinite series. I say we give it a little practice here in a short example. Let's say I give you this sequence. It might look familiar because we just saw it. 2 things I want us to do. Part A, write an expression for a sub n and find its limit, and then determine the sum of the infinite series. So let's focus our attention on part A. We probably can come to the really big number. And what that will enable me to do is to find a formula where 2 to the n seems to be the denominator in each of those partial sums. And then for the numerator, 1, 3, 7, 15, we would just subtract 1. So sums, but now I get a big number, which we know to be 0. Now, if we move on to part B, a little bit more exciting question. Those partial sums. And then for the numerator, 1, 3, 7, 15, we would just subtract 1. So there you have it. Now you could just split this thing apart very easily. Realize that the first term is 1, and when you
terms of t. So if you input all the possible t's that you can into these functions, and then plot the corresponding x and y's for each t, this will plot a curve in the xy plane. What I want to do in this video is figure out the first derivative of y with respect to x and the second derivative of y with respect to x, and in both cases it's going to be in terms of t. So let's get to it. So first let's find the first derivative of y with respect to x. First derivative of y with respect to x, and we've seen this before in other videos where this is going to be the derivative of y with respect to t over the derivative of x with respect to t. And so this is going to be equal to, well, what is the derivative of y with respect to t? dy dt is equal to, well, let's see, the derivative of e to the 3t with respect to 3t is just e to the 3t, and then the derivative of 3t with respect to t is going to be 3. So I could say times 3 like that, or I could put that 3 out front. And then the derivative of negative 1, well, a constant doesn't change no matter what you do to your t, so that's just going to be 0. So that's dy dt, so it's going to be equal to 3e to the 3t, all of that over, well, what's the derivative of x with respect to t? Derivative of x with respect to t is equal to, well, we're going to have the 3 out front, and so the derivative of e to the 2t with respect to 2t is going to be e to the 2t, and then we're going to take the derivative of 2t with respect to t, which is just 2, so this is going to be 6e to the 2t. 6e to the 2t, and let's see, we could simplify this a little bit. I'll now go to a neutral color. This is equal to, so so this is going to be 1/2, that's 3 over 6, e to the 3t minus 2t. 3t minus 2t. And I'm just using exponent properties right over here. But if I have 3 t's and I take away 2 of those t's, I'm just going to have a t. So this is just going to simplify to a t right over here. So now that we know, we've now figured out the first derivative of y with respect to x in terms of t. Now how do we find the second derivative? How do we find the second derivative of y with respect to x now? And I'll give you a hint. We're going to use this same idea. If you want to find the rate of change of something with respect to x, you find the rate of change of that something with respect to t and divide it by the rate of change of x with respect to t. So what this is going to be, we want to find the derivative of the first derivative with respect to t. So let me write this down. So we want to take the derivative with respect to t in the numerator of the first derivative, which I will put in blue now, of dy dx, all of that over dx dt. Now I want you to, if it doesn't jump out at you why this is the same thing that we did before, I encourage you to pause the video and think about it. Think about what we did over here the first time. When we wanted to find the derivative of y with respect to x, we found the derivative of y with respect to t, and then divide that by the derivative of x with respect to t. Here we want to find the second derivative of y with respect to x. Actually, let me just write it down out here a little bit clearer. What we really want to do is we want to find the derivative with respect, let me write it this way. When we wanted to find the derivative with respect to x of y, that was equal to the derivative of y with respect to t over the derivative of x with respect to t. Now we want to find the derivative with respect to x of the first derivative with respect to x. And so everywhere we saw y here, replace that with the first derivative. So this is going to be equal to, in the numerator, the derivative with respect to t of dy dx. Notice this was the derivative with respect to t of y. In fact, let me write it that way just so you can see it. So if I clear this out, e of this could be over this. We can write this as, let's see, 1/2 divided by 6 is 1 over 12, and then e to the t minus 2t. Which is equal to, we could write this as 1/12 e to the negative t, or we could write this as 1 over 12 e to the t, and we're done. So here we have a set of parametric equations with respect to x of the t. Actually, let me read here the first time. When we did all of that over dx dt. Now, I want you to, if it doesn't jump out at you why this is the same thing that we did before, I encourage you to pause the video and think about it. Think about what we did over here the first time. When we wanted to find the derivative of y with respect to x, we found the derivative of y with respect to t, and then divide that by the derivative of x with respect to t. Here, we want to find the second derivative of y with respect to x. Actually, let me just write it down out here a little bit clearer. What we really want to do is we want to find the derivative with respect, let me write it this way.
It says first we have to calculate the derivative of y with respect to x, but again, we know the derivative of y with respect to x is the derivative of y with respect to t over dx dt. Okay, well the derivative of y with respect to t would just be 5t to the fourth. The derivative of x with respect to t would be 3t squared plus 1. All right, easy enough. So that's our dy dx. And it says to calculate the second derivative, it says I have to take the derivative with respect to t of dy dx, which is 5t to the fourth over 3t squared plus 1. And it says I divide all of that by the original dx dt. And dx dt we just calculated was 3t squared plus 1. So it's not like a normal second derivative. You don't take a derivative and then this thing you just take the derivative again. You do that, but that goes in the numerator and you have to divide by the original dx dt. So in the numerator, I'll just use the quotient rule. So it says you get the bottom, 3t squared plus 1 times the derivative of the top, which is 20t cubed, minus, so the bottom times the derivative top minus the top, times the derivative of the bottom, which will just be 6t to the first power, and that's all going to be divided by 3t squared plus 1 quantity squared. Alright, so scoot that over, make our fraction look a little better here. 3t squared plus 1. Alright, now it's just a matter of cleaning up this fraction here a little bit. So let's see. So we can move the 3t squared plus 1. If we flip and multiply, we'll end up getting the denominator to be 3t squared plus 1 cubed. And then we just need to simplify the numerator of our fraction here to get our the simplified form. So if we distribute, we'll get 20 and 3. That'll give us 60t to the fifth plus 20t cubed minus, whoops, how about 30t to the fifth. And obviously we can simplify that down a little bit further.
When we want to find the derivative with respect to x dx, we're going to get the daunting and e of this on half, and the derivative with respect to t of e to the t is just e to the t, and so that's going to be over the derivative of x with respect to t, which we already saw is 6.
Make sure you put your hoodie on.
Yeah, I got you.
This necklace to him.
See, 1 half divided by 6 is 1 over 12, and then e to the t.
In assignment 4B, there's a question.
How do you turn off the alarm clock? Because it keeps going off when you get a call.
Yeah, I can turn it off.
How do you prevent it from coming on?
You turn off in the settings. Yes, sir. I know. I'll turn it off. I didn't bring my Garmin today.
Because tomorrow you can see it be off.
That asks you to use either a graphing tool or a spreadsheet to determine for what values of a does the function b to the minus x squared plus ax squared have no inflection points. You may have a slightly different